So this is the second lesson we got on hypothesis testing with discrete variables, what we started last time. Example 3 is all about a drawing pin, or several drawing pins. And we know that the probability of a drawing pin landing point up from lots of trials in the past is 0.35. What happens now is that 400 trials take place, and in those 400 trials 150 times it lands point up. 153 times is correct. Sorry, I said the wrong thing, I think. 153 out of those 400 times it lands point up. So what we are testing here is, I think these may be a new batch of drawing pins, these 400. So what we're doing here is we're testing at the 5% significance level whether or not the probability of landing point up has changed and is now greater than 0.35. So that's our scenario. Historically it's been 0.35, new batch of drawing pins has come in, 400 of them have been thrown on the floor, 153 of them they came point up. We want to know basically whether the point up probability has changed or not. So first of all, what distribution are we dealing with?
It's changed or got greater?
It's greater.
Okay.
Greater. What did I say changed? Made greater. Okay, what distribution is this reminding you of?
Binomial.
Binomial. Okay, so x is going to follow the binomial distribution, where x will be the number of point-up pins. So x here will be binomial. What will my two parameters be? 400, that will be my n, and my historical p, 0.35. Okay, and that is the p there that always comes from your null hypothesis, which is basically your old data. So I ought to then write down what my h naught is. My h naught is that nothing has changed. P is still 0.35. We were told in the question the alternative hypothesis is p is greater than 0.35. Then the methodology we were using from last lesson was we were trying to find what's the probability of getting what we saw, or even more extreme of that. So what we have to do to work out what we're going to do is find the probability of 153 or more point ups under the conditions of h naught. So what I want then is a probability that x is greater than or equal to 153, and I will use my binomial distribution 400 0.35 for this calculation. Right, any comments?
Do it normally.
Yes, that's right, okay? Because this is so big, you will need to use a normal approximation. Okay. So, the normal approximation, if you're going from BNP...
Would we lose marks for doing it normally? Because I can just use... Okay.
So your calculator will just do that now, will it?
Sorry, lose marks if we do a binomial.
No, will your calculator deal with that binomial probability with those numbers?
So,
Yeah. Yes.
Okay, then unless it's said in the question using a suitable approximation, no, you wouldn't. In the old days, it just wasn't practically possible to do that. So, binomial NP, what does that change to for the normal distribution?
NP and then NPQ.
Yeah, NP and then NPQ, where Q is 1 minus P. So here then, we're now going to be saying, just going to move this up a bit, that X is now normally distributed N times by P, N times by P times by Q, and that is 114.91 apparently. So I want the probability that X is greater than or equal to 153. Any comments? Yes, you do have to use continuity correction, that's right. Because we were going from something that was discrete to something that's continuous. That was true for the binomial distribution, but I now need to use a normal thing here, so I need to change this. I need to use from there to there the continuity correction. So I wanted 153 or more. What will I change that to be for the normal distribution? Is correct, because that would include 153, and it was strictly including 153 there. So that's correct. Okay, where would we go? Where would we go from here? Yeah, that's right. Flip it around to a less than. We don't like greater thans. So it's 1 minus the probability that x is less than 152.5.
If you wrote greater than or equals on the normal...
That would make no difference due to the Biddy principle. Yes?
If you were to use your calculator and just changed it once into binomial,
Yep.
you get 1 minus the probability, but that it's changed to greater than to less than, whatever.
Yes?
When you're doing a binomial, what changes again? Well, does it change instead of being 153, so you're at 152?
If you did it on the calculator using the binomial, you would stick with 153.
Okay.
Because you're not going to you're not approximating it by a continuous distribution, so you just keep it in there. Be interesting in a minute to see what your answer is for the binomial compared with the normal approximation. Right, we've got 4 or 5 minutes left, so if I tell you now, that works out to be, here's the phi calculation, 152.5 minus 140 over root 91. That comes out to be 1 minus phi of, if any of you have done it, 1.310. 1 minus 0.9049 comes out to be 0.0951, which is about 9.5%. I don't know what you got if you did it on the binomial from your calculator. Calculator binomial. What did that give you if you did it on a calculator? Anybody managed to do that? Didn't in the end. Has anybody done
I
it?
got, I think, about the same. Yeah.
About the same thing.
I'm doing that.
I'll leave that up to you.
So what conclusion do you...
Right, well, let's have a look. So what we've said here, the probability of getting what we've seen, well, there's a 9.5% probability that we would have got that by chance. So, as that probability is not less than 5%, we will accept H0. It could have just happened by chance with a 9.5% chance, so we'll accept H0. So we will conclude that, it's not mu here, is it? It's P remains at 0.35. There's nothing to change our minds on that.
I've got 0.0956.
You got
956.
Okay, so you're out by one figure in 2 significant figures, aren't you?
Yeah.
So yeah, that's very close. Okay, put that in there, thank you. So that's what you would have got as a binomial. So there we go. We've got one more example to go, which I think we'll probably save for next lesson there, because we've only got about 2 minutes left.